My name is Łukasz Langa, and what you've just heard were two hardware synthesizers being played by AsyncIO. I was just twiddling some knobs to make this maybe a bit more interesting. I come from Poznań, Poland, a friendly city in Central Europe. Come visit when all of this is over. It's located very close to Berlin, also Warsaw. The connections are pretty good. In the meantime, feel free to reach out to me online to talk about Python, music production, role-playing games, or muscle cars. This picture is from back when we still had hairstylists. Crazy times, crazy times. Today, though, we're going to discover how AsyncIO can be used to process MIDI to drive hardware synthesizers. And to make things a little more interesting, we're going to do it live. Or we were supposed to do it live, but now you're on YouTube watching this video. So to keep things interesting, we're going to do it from scratch. So we're going to talk about synthesizers. There's very many kinds of them. This particular one is a modular synthesizer, meaning it consists of many independent modules connected together by wires. Every single module has a very specific role, and connecting all of them together creates unique instruments. There's probably no two modular synthesizers that are exactly the same. The two modules that you can see on the bottom are produced by Moog. Some of the modules on the top were either bought or assembled by me. And the Ornament and Crime in particular, with the nice squiggly LCD screen, runs a firmware that I modified myself. So it's actually like a very interesting hobby for programmers because you have very low level, very end-to-end kind of influence on what the music is going to sound like. Before we get to this kind of advanced stuff, though, let's focus on a different kind of instrument. What we're going to use today is a Novation circuit. It's a groove box, meaning it is an entire small music studio all on its own. You can create full musical tunes just with this particular piece of hardware. But it's production grade. Actual musicians do this, do use it for live acts. And in fact, Novation hardware is being used by Aphex Twin. So this is legit. But at the same time, it is a very fun instrument. What you can do with it is you can take it anywhere you like. It actually runs on batteries as well as has its own puny speaker. So you really don't need anything else than just the circuit to make music. For today, we're going to be using this groove box as a drum machine. But it would be a bit boring to just have drum sounds in our presentation. So we're also going to use the Novation circuit mono station. This is a monophonic analog bass synthesizer. And what that means is it plays bass, low frequency sounds. It is monophonic, meaning it plays one sound at a time. And it's analog, meaning there is literally an electric oscillator that creates sound that through some path that we can control with the knobs ends up in your speaker. So having an analog electric synthesizer makes it imperfect. It is vulnerable to changes in temperature and humidity. There is always some electric and magnetic bleed through between the different electric circuits that are in a synthesizer like this. So it's imperfect. But that's actually a good thing. Very often people like analog synthesizers specifically for their warmth and the richness of the sound, which is created with this, kind of inherent randomness of the environment you're in. So we're going to be using those two. They're going to provide us with plenty of musical opportunities already. There's going to be a drum machine and a bass synthesizer, drum and bass, even though we're not going to be particularly interested in that particular music genre. So I was ready to present all of this to you live, but it turns out since this is impossible, I need to record the video now. And this is what I'm looking at right now. So the entire setup to make a video is quite different from just giving a talk. I was surprised to discover that it is actually quite more work to do this effectively. And kind of you have higher expectations for yourself in terms of delivery as well. One of the things I planned for the presentation, but I decided not to overdo, was to make a little intro to AsyncIO while doing all this. However, it turns out that that would be rushing through things, and I wouldn't be very satisfied with this, and neither would you. If you are new to AsyncIO, you would feel like that went way too fast, like it explains very little. So instead, what I'm suggesting you do is you can direct yourself to the HDB's a YouTube channel where we created a series of videos that introduce AsyncIO in a manner that is catered towards people who are new to both AsyncIO and asynchronous programming. So it takes its time. There's multiple episodes that go through all sorts of parts of the AsyncIO both framework and the style of programming that it encourages, that it supports. So to subscribe, just go to hgb.com/YouTube. You can watch some of those videos there already. I highly encourage you to do so. Like right now, if you haven't seen AsyncIO yet, you can just pause this video, right? Like, that's one advantage of doing it this way. In the meantime, if you already used AsyncIO, let me just do a very quick recap. So we are using coroutines in AsyncIO, which behave pretty much like regular functions. You can read them from top to bottom, and they execute instructions. A very special instruction that we see is the await instruction. That means we're waiting for something external. And in this time, Python is able to use that time to do something else, in the meantime, now that we're still waiting. So coroutines compose together in what is called cooperative multitasking. And thanks to this availability, in this particular slide, you see that we can await on AsyncIO sleep. However, the main coroutine still says await callback 1, await callback 2, await callback 3. So it will execute from top to bottom, one instruction after the other. But with AsyncIO, we have special powers. We can make those things happen at the same time. To do this, you use the gather function to tell AsyncIO that please start executing all of those 3 coroutines right now and gather the results as fast as possible and present to me like as soon as you have them. So that's pretty much the extent of AsyncIO that we're going to be using today. Now we also need a little bit of music theory, not much, just enough to get by. So music is all about pitch and rhythm. Pitch means, how high the sound that we are hearing, like voice or a synthesizer, sounds, right? So like typical female voices are going to be higher pitched, they're going to sound higher, right? And typical male voices or bass synthesizers are going to be lower pitched, they're going to sound lower. In this particular slide, you see a grand piano keyboard where sounds go from lower pitch to higher pitch, and the sheet music notation equivalents. Like, don't worry about the sheet music notation. We're not going to be using it. I just wanted to show you that this is just an alphabet, a way to describe what particular note you mean. So if I were to actually play the notes that you can see here, C, D, E, F, G, A, B, C, that would sound something like this on the synthesizers I have with me. You can see this is not exactly a grand piano keyboard, but there is some resemblance of how all of this looks like, right? Like that row would be the white keys, and this shape right here like reminds us of the black keys on the grand piano keyboard. So the only thing that we need to add here is that every 4 notes here on the sheet music notation, you see a vertical bar. That literally denotes that there is an end of a bar of music, an entire note has been played. Every note that we have in the shape that we have here is a quarter note. So 4 quarter notes is our kind of timing that we are using for this particular piece of music. So that is useful because you can have not just quarters, but 8s or 16s, which go faster. You can fit more of them in the same bar and whatnot. This is essentially it for the music theory. The most interesting part now is how all of this connects together with MIDI. MIDI is one of the few examples that I know of in history where there was a protocol invented by a bunch of music hardware vendors in the early 80s. And that standard is actually very good and very well supported across the entire industry. So you can buy different kinds of music hardware today, and they pretty much all of them, if they are electronic, support MIDI to some extent. Of course, there's going to be differences between implementations, and some of the vendors are going to use some more advanced functionality, and that advanced functionality might differ between the 2 devices of different vendors, or even within the same vendor Again, different models can behave a bit differently. But the basics, like keeping the same tempo, like playing notes or stopping to play notes, and so on, like that is very well supported by each producer, but by each vendor. What is great about this is that you can pretty much expect that if you have a digital audio workstation like Logic or Cubase or Ableton Live, you will be able to use any hardware that you buy with that audio workstation, which is pretty sweet. Historically, we've used DIN5 cables that you can see below me on the picture. But the thing is, like those were vulnerable to like the cable length, causing corruption of the data that is being sent. Each cable was just single directional, or in other words, unidirectional. You could only send the data from point A to B, not the other way around. So to connect two devices in both directions, you needed two cables. And, connecting even more than two devices made a complicated mess of cables. So we're not doing this anymore. What we're using these days are USB cables. And in fact, the synthesizers that we have here have this as well. Like you can see the yellow cable right here is the USB MIDI cable for the mono station, and the blue cable here is the USB MIDI cable for the circuit. In fact, now that I'm talking to you, I am recording what is happening in the mic that gathers my voice, as well as the instruments that we're going to be playing in 3 tracks in Ableton Live. So if I play a note on the blue circuit, you will see in a second that it actually appears in the wave, and same with the mono station right here. You will see that the notes actually appear. Ableton Live is used to mix this, so I can actually gather all of the events that are happening and then kind of overlay them over the video. But I'm not doing any more trickery here, right? Like there are no sequencers from Ableton Live that we're going to be using. There is no musical post-processing or any other overdubs. Everything that you're going to be hearing comes directly from the instruments themselves and is sequenced by Python. So coming back to our presentation right here, MIDI, amazing, we can use it, but how does it look like? Well, fortunately, the protocol is amazingly simple. It is a synchronous protocol, meaning that if you have points A and B connected, as soon as you send information, a note on, when the instrument receives that message, it should play the note. There's no scheduling, there's no saying, please do it in the next bar or on Tuesday or whatever else. Like it's synchronous, you should react to messages that you get as soon as they arrive. It is still a unidirectional protocol, meaning the USB MIDI cable has virtual MIDI in and MIDI out ports. So any single cable, you can pretty much rely on the fact that nothing it has to happen in 2 directions. And everything that does happen needs to happen as fast as possible. So if you need something to happen later on, you just wait and send the thing later on. There are different kinds of messages that you can send. So note on would mean that if we have a keyboard, like press the key on the keyboard, right? Note off would mean raise your finger from the keyboard, right? So typically, the longer you keep a note, the more sustain you have. If you keep your finger off the key, the note is going to die off. You can also use different notes, so C1, E2, F1, and whatnot. They're numbered because there's different octaves, so there's more than just 12 notes. C1 is going to be lower pitched, and C2 is 12 notes up, and C3 is going to be another 12 notes up, and so on and so on. Velocity is how hard you hit the key, right? So typically that means the more velocity, the higher volume of that particular sound generated by that particular synthesizer. The last thing that you can see on the picture here is the channels, right? So many instruments can support more than one sound at a time. This is great because that means you can either have multiple instruments, kind of in the analog sense playing together, or you can say, I just want to do drums here and like some grand piano right there. So drums are typically on channel 10 and the other channels depending on the instrument. So how do we agree on how fast we should be playing together? Well, we do this by a clock signal. The clock signal is sent 24 pulses per quarter note. What that means is that the quarter note that you saw in the sheet music notation on the music theory slide, it has like 24 signals that denote, how fast this thing is going. That is plenty of resolution to make sure that the entire ensemble of your synthesizers, hardware and software, play synchronized at that same speed, right? So they're like a very good band. They are going to be in sync playing together. In fact, the intro music that I showed to you was being played by our MIDI program, the kind of program that we're going to write now. And that program is still running right here. You can see that 248 is the particular byte number for the clock signal. So there's 24 of those, there is a stream of them coming very quickly this way. We're not actually going to be using the intro program anymore, so let me use this opportunity to just close it off. All right, it's aborted, it is shut down at this point. So you've already seen a console, so you're probably excited about actually, me stopping talking and introducing some code. So what we're going to do next, we're going to actually make Python tell the both instruments I have with me what sounds to play and when. To do this, to achieve this, we will be using some clock, right? We need to agree how fast we should be going. And we could either make just AsyncIO be the clock, count, how fast we're going. But it's actually more interesting to explain to you and to show you how we can use one of those instruments as a clock source. What that means is we're not going to be clock sources internally in our program, but we're going to react to an external tempo and just adapt to it. This is actually very important because this makes the program that we're going to write not a toy. It's something that you can use in actual music production because you will for sure want something else and not your puny Python program to be the clock source. Typically, it's going to be some kind of digital audio workstation like Ableton Live. But if you are into hardware synthesizers, like the modular synthesizer I'm building and whatnot, you could make some of those modules the clock source for you. And the Python program would only be following that clock. So in our case, the Novation circuit, as I said, a full-grown Groovebox is going to be our clock source. We're going to feed it to Python, so Python knows how fast it should be going. And then, thanks to this, we will be able to sequence, to generate notes in a given sequence, both of the instruments. All right, so that's it for the slides part. Let's move on to the more interesting things to be done. So actual Visual Studio and our coding. This particular screen here is not very interesting because that was the example that I started with, the intro music. Let's go ahead and switch to some starting point that we will be using to recreate a program like this. We're going to be going from scratch so that you understand what is going on and how we achieved the design that we are actually finishing with. So let's just say we're going to be starting with P0, which is PyCon's 0th starting point, right? Okay. By the way, if you would like to actually follow me with your own program and your own hardware synthesizers at home, you're absolutely invited to do this. The entire code lives in a Git repo on GitHub under my account, AMBV. The project's name's AIO Tone. So all of this is available for you if you are ready to dabble with this yourself. But now we are starting at P0. We're literally starting with a file that is just some very, very simple boilerplate. As you can see, it's just a bunch of lines. It doesn't do anything yet. The only thing that I don't want to start totally from scratch is a MIDI PY file that pretty much consists of some mappings between the names of bytes and the byte values, right? So obviously MIDI on the wire is just a bunch of numbers like anything else in computer science, but it is just more natural for humans to kind of assign names to them. So I already did that for us. We're not gonna have to, come up and find the numbers and the names for them later on. We already have all this. And then some boilerplate to just get the MIDI ports for our Python use. We're going to be using RT MIDI to actually do the heavy lifting of sending things and receiving things from the MIDI hardware instruments. So, as you can see on the slide, this is actually not the most complicated code out there, but it had to be written. So we already have the wrapper right here, which is going to do it for us. So that is not very interesting. The more interesting thing is definitely the dunder main file, which contains, will contain our sequencer. So at this particular stage, nothing interesting is happening yet, right? We have our main function that we are calling if this is being called as a script. But that main function is already a click command. And why do I do this if I don't have any arguments to parse? Well, click is something I use every time that I'm doing some script that is going to be invoked from the command line, because it is much more than just command line argument parsing. What it's also doing, it provides you a sensible way to echo things on the console, regardless of the console's configuration. In this particular example here, it's already a styled echo. So what it enables us to do is also color things, like, say that this foreground should be red, and this should go to standard error and not to standard out. So I like click a lot and use it a lot for more reasons than just command line argument parsing. We can also raise aborts, which will generate nicer exit messages than just a full trace back of things that can happen, right? So that's for click. And now, the only thing that we need to do is use the AsyncIO framework's run function to use our async main. The async main async function so far doesn't do anything much. It gets the ports for the circuit and for the mono station. So it would be actually maybe better to just have it actually do something interesting. So my first attempts at recording this video were me typing everything out and explaining as I was going through it. But I found this to be both too slow and too awkward whenever I made a typo or whatever. So this time we're still going to be doing some typing, but most of the kind of less gradual changes are going to just happen by me checking out another tag from the repo, so that there is something more for me to talk about and less opportunity to, show you how bad I am at typing. So the first thing that I wanted to show you is that you should be using a more interesting event loop, right? You can already see Visual Studio Code helpfully highlighting the changes that just happened here in green. So you can see that those are just the 2 lines that changed. So UV loop, I'm importing something and installing it, but it doesn't explain what that is yet. So let me do that for you. The event loop that AsyncIO is using is a reference one. It is written in Python and it is designed for correctness and ease of explanation, right? So you can literally go inside the event loops code and understand how AsyncIO works internally. This is also great for debugging when things internally in AsyncIO are not working correctly. It is easier to kind of step through things as they happen and understand what went wrong. However, when you're running things in production, what you want is maximal speed. You want maximum performance. So for this, we're going to be using Yuri Solivanov's UV loop library, which wraps libuv, that same event loop library that is used by Node.js, and allows it to be used by AsyncIO. You don't actually have to do any hard setup to make that happen. The only thing that you need to do is call UV loop install and you're done. So having this out of the way, let's move and see the next thing. And the next thing is this. We have a callback that we need to set whenever we want to get MIDI information from a MIDI import. You can see in lines 14 and 15 that we got pairs of ports for both the circuit and the mono station, right? So the from circuit is actually information coming from the instrument, right? And to circuits is an opportunity for us to send it notes and other events ourselves. Same with from mono station, information that we're getting from the mono station, and to mono station are notes that we can send to it. In our particular case, what we want to do is we want to receive the clock signal from the circuit. So we will need to register a callback to make sure that every event that comes from the instrument is being received on the Python side. From mono station, we are in fact closing. We're not interested in anything that comes from this particular instrument. This is important because RT-MIDI has its own internal buffer. And if we actually did not close the port, it would quickly fill up and RT-MIDI would be unhappy with us that the buffer is full and we never started getting information from it. So here we're setting the callback and we're closing the other port. Everything is good, right? Well, except for the fact that there is actually not a MIDI callback function yet. We didn't implement it yet. So we need to fix this. We should probably also fix the name of the MIDI callback because it's super non-descriptive. Doesn't say what it will do. It just says what role it fulfills, which is a rather poor name. But let's stick with it. We only need one for this particular demo, so this is not a big problem in our particular case. So the MIDI callback that we will use here is, in fact, taking a MIDI message in the format of a MIDI packet and an event delta, some other optional data that we're not interested in this particular example. It doesn't return anything, but you can do whatever you want in this particular scenario, right? Like you have a MIDI message which already says us whether it's a clock or it's a note on or it's a note off, and a delta saying how much time did pass between the last MIDI message and the current MIDI message, right? So the nice descriptive names that we see here are actually by me. I just decided to apply some human descriptive names to raw types that are in fact used over the wire because typing is for people, right? You are using it as a form of documentation just so that you can understand what is happening when you're returning to your own program 6 months from now. Or if you're working in a bigger team, everybody can agree. It's like, oh, okay, even though this is a float and this is a float, this particular one is an event delta and this particular one is a timestamp of the current time. So this is in fact what we're going to be receiving from the MIDI, from RT-MIDI, right? The callback is always going to get those arguments, so we can do something with them. In this particular example, like we are building this as we go, so there's nothing happening yet. I only recreated the MIDI packet and event delta, unpacking the tuple that we're getting here, and already set the send time to the current time. We're going to be using this as a MIDI message in the next step. Like now, Flake8 is actually unhappy with me and not using send time yet. Don't worry, Flake8, we're getting there real soon now. So switching to P4, you can see that there's already something that is happening. Like what is happening now is we introduced a queue. Why did we introduce a queue? Let's switch away from the code for a second to talk about how RT-MIDI does the callbacks and why we need something like a queue to process those things with AsyncIO. So when an instrument like the circuit sends information to us to a port, what is actually happening is that the hardware driver of that particular port is getting its data and just publishes it on the operating system for any subscriber to connect to. So if you're subscribed at any given moment to those messages, you're going to get them. So RT-MIDI, through our port opening, when we're saying we want the circuit port, it subscribes to this stream of messages, right? And the thread of RT-MIDI, which is written in C++, is reacting to new messages. And has to somehow allow Python to get those messages in Python code. And this is why we were setting up the callback, right? The callback is essentially a function that we give to just say that, hey, whenever there's an event, run this Python code. But callbacks are rather unwieldy to use with more complex programs. Like, so designing more complex programs on callbacks is a rather hard problem. More importantly, the C++ thread where all of this receiving is happening is a separate thread from the rest of Python for us. So we don't actually want to do any heavy computation there. We would prefer to do this in a separate Python thread that we see here. And that particular Python thread nicely runs our AsyncIO event loop. And on that end, on the event loops end, we're just going to run queueGet to get the information from the queue as it goes. If we are awaiting on that queueGet, if the queue is empty, that is going to block until there is something new available. So whenever C++ puts information there for us, the queue is going to get more elements, and Python is going to get those elements out to be able to process them. So that's essentially the design of the flow, right? In a nice slide, but it is not super kind of verbose in code either. You can see that here, essentially what we're doing is the information that we got, we format it as a MIDI message that agrees with this particular MIDI message type that we defined here. And the only thing that we need to do is put that message on the queue, right? So how do we make anything happen, any music play? We also need to await on some MIDI consumer. And that MIDI consumer is going to also use that same queue that we defined here. It's a queue of MIDI messages, right? And it's going to consume whatever comes on that queue. How does a MIDI consumer work? How does it look like? It is literally something that just loops over forever, right? While true. And while looping, it is going to await on queueGet, as I promised, right? And once there is a new message on the queue, it can do something with it. In this particular piece of code, the only thing that we're doing is printing out whatever we got as a form of debugging, right? So we're printing out the packet, and we're printing out the event delta. It's a float, so we're formatting it just a bit so that it's not super unwieldy. Same with latency. And latency is measured in our case by the difference between the current time and the time at which the element was put in the queue. The latency is just fine for our purposes. I'm in fact showing this explicitly just so that you can relax and see that AsyncIO is plenty fast for MIDI applications. So this is the main flow of information that we're going to see from the circuit. But it is a bit naive now. And if I tried to execute this right now, like weird things would happen. So to make things a little less naive, what I will have to do is to run P5. And now you can see that there are, in fact, a little bit of changes here, right? We received our AsyncIO event loop. What did we do that for? Well, to instead of just saying queue put no wait with our MIDI message, we are saying a loop, call soon. So as soon as you're ready, call soon, thread save, queue put no wait. Why is that thread save here as well? It's a variant of call soon, which can be called from other threads. And if you remember correctly, the C++ thread in which RTMIDI is listening to messages from the circuit is separate from the main Python thread in which our AsyncIO application is running. So we need to use call soon thread save for everything to stay sane, for everything to stay stable. On our MIDI consumer side, nothing much has changed yet. So we can attempt at running this right now. Let's see how we do this. So this is in the AIO tone package. It's called dunder main. So what we can do is just say Python m AIO tone and run the application. Oh, and you can already see a stream of events in AsyncIO that are processed by our MIDI consumer, even though they are received in a separate C++ thread by RTMIDI. So our callback every time is responsible for receiving this information, and totally separately, this information is gathered from a queue and processed event by event. So that looks good. Let me try to shut the application down. That shut down, everything is good. But if we try to do this a few times, we might sometimes see that there might be actually exceptions or other weird things happening. In this particular example, of course, as I'm trying to demonstrate this, that will never happen. But believe me, this is not how a production application should look yet. So let's introduce some form of error handling. There needs to be just a little of that. So let's see what we changed now. Again, helpfully, a Visual Studio Code will show us what lines changed. So here we just wrapped the callsoon thread safe in a try except block. We're actually looking for base exceptions because one of the very typical ones is going to be a cancellation error and other things that can happen when our Python thread already shut down the AsyncIO event loop and whatnot. Whereas the MIDI callback running from a C++ thread doesn't know about this yet and tries to execute our Python code. So we're wrapping it just saying, hey, callback failed, like we couldn't call that thing soon. We couldn't schedule that callback anymore. On the consumer end, what we want to do is when things get canceled, we will ensure that the C++ thread unregisters our MIDI callback. If we didn't do this, it would just keep sending information to us, and that would sometimes call the exception that I tried and failed to show you. We are also using some magic silence functions on both of the two ports. They kind of already are there for our future use, but to explain why they're there. As you saw before, there are separate note on and note off messages. So if we stopped our application in the very worst moment by just saying note on, and now we stop, that note would be playing forever, which would be super annoying to anybody. It would be actually quite tricky to make this stop playing. So we want, whenever our async main is canceled, and is going to be canceled, for example, when we Control-C our application, we want to make sure that we are canceling the callback at the same time, and we are silencing both instruments, right? So if there were any note on events, we will counteract them by saying stop playing and all notes off on all channels, please, right? So this is going to do this for us. So that is actually enough right here. And again, if I executed this now, it would look pretty much the same. Even though we're getting information from the circuit, nothing interesting is happening yet. So let's finally make some sounds happen. Like we're recording for like a good 35 minutes already. Let's make something sound from the program that we're writing with now. So if we get MIDI messages from that MIDI port from the circuit, there's going to be many kinds of them, and we can process them by type, right? We can check what kind of MIDI message we're going to encounter. And in this particular example, the clock message, the 24 pulses per quarter note, is the particular example that we need to keep things in sync. So what are we trying to keep in sync? Well, first of all, we need this clock for our Python sequencer, but also we have two hardware synthesizers. The circuit already knows what its own internal clock is, but the monostation is a separate hardware synthesizer. It doesn't know what tempo it should follow. So here, whenever we have a clock message, we also want to send it to the monostation, to the base synthesizer. Same with start playing and stop playing messages. We also would like those messages to be forwarded to the monostation. But wait a minute, if we actually save the file right now, you will see that Flake8 is unhappy with us that this base variable doesn't exist. There was no base argument. But if you're already thinking forward, you're going to see that there's not only going to be a base synthesizer, there's going to be the circuit, and there's also going to be probably more data, more information that we will need to make our program tick. And annoyingly, we could just keep adding more arguments to our function, but soon enough, like that would be unwieldy and very big. So instead, what we are going to be doing here is we're going to introduce a class to keep our state. And since that state describes a live performance, we're just going to use a name performance for our class. So that class for now only has 2 attributes. So we're using a data class for it so that we don't need to write a dunder init method and dunder wrappers and equality comparisons and anything else. But in fact, we are using the pro version of data classes, which are adders. You can just pip install adders to get those as well. So behaves pretty much the same, but has plenty of other functionality, some of which we're going to even be needing right now. So cool. We have a performance object that holds, for example, our MIDI outputs for now. So the only thing that we need to use that is to instantiate the performance object right here. So our drums are going to be our MIDI out port to the circuit. That's going to be our drum machine. And the bass is going to be our mono stations out port. So that's it. We only need to pass it to the MIDI consumer right here. And now Placate is happy. There is nothing crazy happening here anymore. We can performance-based send message, right? Start playing. So in fact, we can already demonstrate that this does something. Let me show you. So here you can see, 2 octaves of the instruments. We can change the view just a little so that we see just 1 octave at a time. And when we do, you can see that those instruments also have their own internal sequencer. So it has 16 steps. You can see them as well. If we run our application right now with, again, -m AIO tone, the clock is ticking. That's this clock right here. And if we start playing here, right, you will notice that both instruments started playing. We did that. Our code did that. We are now forwarding the clock messages and the start and the stop messages between the 2 synthesizers. So if we stop, you're going to see that both of them stopped. If they're going, they're started at the same time, and they're going to be stopping at the same time. Like you can actually see that the play button here gets bright green when it plays, and so does this one, even though I'm not pressing it, right? So they are, in fact, in perfect sync, which is great. In fact, you can change the tempo right here, like 130 in this kind of lo-fi display here composed of those buttons can be changed to be not just 130. We can make it or 240. You can see that this sequencer right here now goes faster. And if we go back and just do a very slow tempo, you will see that the sequence advances way slower. So this is great. We are, in fact, already doing productive network programming with just MIDI, right? Which is a very simple networking protocol using Python, but interacting with actual music hardware. But still, I promised you sounds, and there were no sounds. Let's fix that. So now finally we are introducing a very low-level drum machine. It doesn't have any tempo sync yet because that would be a little too much for just the right moment to explain this. We're going to be building on top of what we have now just in a second. So what is the drum machine? Well, if we press play, the start message is being sent, right? So we already had this code and this code and this code there already to synchronize our clock with the other synthesizer. But what we also do now as a new feat is to create a task for the drum machine if no task was created yet. And if we press stop, we would like the task to be cancelled, the drum set to none. And again, just as if we canceled the entire program, we want to silence the drum machine. So that is actually how you would schedule tasks, background tasks, to run on AsyncIO regardless of application. So if you have networking applications, you would do the same. If you want to do sub-processing in the background, you would do the same. So this is a reusable technique right now. Create a task. That task is just a coroutine. And if you're done with it and it's actually running forever, you can cancel it. But some tasks are going to actually have a natural end. You would expect them to return some value or whatnot. In this case, you can just join those tasks, wait for them with other AsyncIO functions to gather the results that they received. So create task. What does it actually create? Some background loop that we are using here. That background loop is very simple. Even though there's just a few lines here, the lines are kind of required because there is a note on event and there is a note off event, right? We always want to lift our finger from whatever keyboard we're using. So in this particular example, we are playing a note on event on a given channel of a given note with a given volume. Then we are going to wait for some time, and we're going to lift our finger again with the same configuration, and again wait some time, just so that the events are kind of spaced out evenly. The channel that we're playing on is MIDI channel 10. Like it's 9 because it's numbered from 0. That's usually drums, like pretty much in any MIDI implementation out there right now. Note 60, so the numbers are just, from 0 to 127. Note 60 is just a bass drum on my particular drum machine. Those numbers actually will be different between different drum machines. You pretty much have to try this out yourself or read the manual, but who does that, to learn which drum is which note. In this particular case, 60 is going to be our bass drum. Volume 127, pretty loud. Okay, excited to actually hear how it sounds like? I am. Let's do it. Okay, nothing is happening. Why? Because this thing controls our performance. We need to press play. So partial success. We can hear that there is a bass drum sound in uniform speed, but that speed is not really the same as the speed of the sequence, right? And if we change the tempo here, that does nothing. Actually, you can see that the tempo should be changing, but our coroutine so far is ignoring the changes that we're doing. So let me just go to 130 right here. Why is the tempo not changing? Well, because we're just sleeping here for half a second, pretty much ignoring the clock signals for our purposes. The only thing that we're doing with the clock message whenever it comes is to just forward it to the other synthesizer. What we would like to do instead is to actually make use of it in our code. So the simplest way to do this would be to just record the time that happens between two clock messages, and doing this kind of record a delta, which is going to help us calculate the tempo. Before we get there, though, one thing that I did here, I see, is I extracted this rather cumbersome, 4-line way to process a single note with a note on and note off to a method on the performance class, because we're going to be playing very many notes very soon from now. So it would be annoying to have to always set it up, using 4 lines every time. It would just look very busy. Instead, by extracting those 2 methods right here, what we are able to do is to sequence notes with a single line each. That is way better. Okay, but let's get back to talking about the timing of events. So to make use of the clock signal that we're already receiving from the circuit, what we need to do is just listen to the clock messages. If there were 2 consecutive clock messages, then RTMIDI already calculated the timing between them. That is the timing without any latency in Python. So that is good timing. And we can just save this as the pulse delta, right? So that's the delta between 2 clock signals. That is cool. We already know that there's 24 pulses per quarter note. So we can start thinking in musical terms now. We are going to be using this pulse delta right here to make sure that we're waiting for a given amount of time every time. So let's see if that particular pulse delta does anything interesting in our particular program. So AIO tone. That already sounds faster, so that is probably a good thing. Can we change the tempo right here? We can. Actually, you should be able to see this as well, right? We're changing the tempo, and our coroutine speeds up the notes or slows them down. That is good. That is exactly what we needed. So now we are ready to actually start typing some more interesting things into our sequencer. Is it actually fun to use? Is it very cumbersome to write any musical code with it? Well, let's see. In my opinion, it's actually very easy. So how would you actually add more notes to it? Well, how about we just add another one right here? Since we already have some helper variables right there, let's say snare drum or closed hi-hat or open hi-hat, we can already do something like, say, snare drum and play for another 24 pulses, right? I helpfully named this pulses here, so maybe let's redo this so that we still know what is going on. So this should already sound a tiny bit more interesting than the last time. In fact, that's exactly what is happening. We hear a bass drum, a snare drum, a bass drum, a snare drum. Cool. So can we make this even more complicated? Yes, and without much kind of additional work. So one particular thing that dance music very often implements is that the bass drum always hits on every quarter note. Here we are just hitting the snare drum and not hitting the bass drum in that particular moment. We would need to fix this. Like, how about we made the bass drum always hit and the snare drum always hit, just hit every second note. So we would want to just have two while loops, right? Like one right here and one that would actually be waiting for us for quite a bit and later on play the snare drum. So to achieve this, we actually cannot write just two loops like this one, because the first one is going to just play forever. We're not going to get to the other one. But what we can do is just create another async def, call this the bass drum, and create yet another one, async def snare drum. And this one will both await on that quarter note, but also performance wait. So just wait 24 pulses for us so that it hits every other note, whereas this bass drum is going to hit always, right? One thing that now the code is going to be unhappy about is that performance does not have an attribute wait. We need to extract it. So now what we were using here is AsyncIO sleep directly, but we also want the ability to just rest and wait for a given amount of pulses. So it would be good to extract this. So let's just stash our changes in the sequencer for now and switch to yet another class right here and pop the stashed changes. So now what we have in our code is both the wait method and the bass drum and snare drum that we implemented. Now, kind of MyPy is happy, but the only thing that we forgot to do, and nothing would happen if we didn't fix that, is that now we have to await on AsyncIO gather to make both the bass drum and snare drum play together. Let's see if that does anything. Okay, you can already hear both the bass drum and the snare drum playing together. But they're playing together, but not really in sync. This doesn't sound like a good drummer. Sounds like a bad drummer, actually. They're sometimes in sync and sometimes they just get out of sync. We don't really know why. So let's think about this. Why would that be? Well, and to answer this question, we need to talk for just a second on clock skew. So what happens in hardware instruments very often, and sometimes that's even in production professional vendored instruments that you're going to be buying, is that if there is agreed upon tempo, right, like 125 beats per minute, if that tempo is agreed upon, but we never agreed on synchronizing when the first beat should be playing, those things can go out of phase. And on top of this, there's going to be micro changes between what is meant by 125 BPM in one hardware instrument versus another. So on top of the phase shift, you can also just have things getting in and out of sync kind of randomly to the musical, kind of ear that we are having. So this is not very good. What we need here is a way to synchronize the first beat to make sure that we are going to get, perfect sync with us. Can we do this? Yes, this is actually not very hard again, and we are going to be using a very fundamental piece of AsyncIO. That piece is called the future. So looking at futures, they are a way to promise somebody that there's going to be a result for us in the future, right? Not yet. For example, if two coroutines, like the left line and the right line in the pictures right there, interact with one another, and the first one doesn't have the result yet, it can give somebody a future instead. And the other coroutine can await on that future. So as long as there is no result ready yet, we are awaiting. Time goes down, right? We are awaiting. And if the first coroutine finally has a result, it calls set result, and then AsyncIO stops waiting on F. It already knows, oh, there's a result. So it assigns the result to the result variable right here, and we can use it, right? So in this particular example, we can see the design of a future. What we actually will want from futures for our purpose is something like this. Instead of just having a wait, just randomly, without consulting anybody, AsyncIO sleeping for the number of pulses, what we're going to be asking for is, please count 4 pulses for me, right? And our kind of metronome functionality will say, okay, fine, I will count 4 pulses for you, returning a future. And now our synthesizer, our sequencer, is going to wait. And it will only receive the result, which we kind of ignore here, when 4 counts passed, right? So the count is 0 right now. So our counter is going to set the result of the future resolved. So that's essentially the design that we need to do. So using futures for synchronization. And this is a rather nice technique to make sure things happen in unison. They obviously don't happen exactly at the same time, but with the AsyncIO event loops resolution, that's plenty enough for our purposes with coding, right? So let me just switch you to the screen where you can see the code. Cool. And let's replace our naive implementation of pulse delta with the metronome that I described to you. So again, let's stash our wonderful, very complicated sequence of drums and switch to another step, which already is using the metronome. So the metronome is something that is going to take a tick from us whenever a clock is happening. The only other thing that we need to do is to reset it whenever we press start, so that everybody knows that we press start right now. So now is the first note. We should be starting from this moment. So it is some metronome class, right? Let's see how this is implemented. It is just a metronome. Every object of performance that we're creating is getting one automatically due to the use of the factory functionality of adders. And that is essentially everything that we need to do. But here, the wait method now, instead of running AsyncIO sleep naively, it is running this wait for X pulses. The architecture of the wait for X pulses you have already seen. That is exactly what I showed you on the slide with, the kind of the design for counting 4, if that would be 4 pulses, and setting a result on the future. In fact, we can see this clicking through to it right here. So for waiting for X pulses, we're creating a countdown, right? And just await on it. So when those kinds of pulses, those numbers of pulses, passed, we're going to return. And in turn, this await is going to return. So everything composes very well together. Everything now works perfectly fine. So the countdown is a subclass of future that does this functionality of just, counting down with each tick. Finally, when the value is 0, let's just set the result and we're done, right? The metronome is kind of like a multi-countdown, by which I mean that it has all the countdowns in our application, so we can multiplex this, right? So there is going to be the clock signal sent from the circuit and just received by us once, and we tick the metronome, but doesn't matter how many countdowns are currently active. With the tick, we are going through all the countdowns, and if a given countdown is done, we're just removing it from the currently happening ones, and that's it. That's something that enables us to just tick in one place, but wait in very many places. So it's a rather short class. You can see it on GitHub if you're interested in more details about it, but that's all the magic that we need here to make sure that our program now is fully in sync. This is already going to be something that kind of has production level synchronization. So let's see if that actually works to any extent. Okay, just one place right now. The snare is not playing because we forgot to unstash our change. And by we, of course, I mean me, but I love to share responsibility for my failures with others. So it's your responsibility as well now. Okay, now we have the snare drum as well. So that's my success because I did that. Let's go. Okay, they're playing. Can we actually go and speed this up and see if they're still in sync? They're in perfect sync, even at 240 beats per minute. They're in perfect sync. All right. So that's it for production level clock synchronization that solves the clock skew. But we still have Flake 8 being unhappy with our sad closed and open hi-hat. So let's just make it happy finally and just create some hi-hats for it. Let's go, Flake 8. We will make you stop complaining right now. So let's await on performance, play drum, close hi-hat, just for 6 pulses. So that's going to be pretty fast. Do this twice, and then now a little longer, we're going to go with an open hat. Nothing would happen if we weren't gathering that thing too. So let's gather it as well. What do we have here? Okay, a very, very typical dance way of interacting with hi-hats. But you know what I'm annoyed at? Like this stream of event notes, which are mostly just clock signals, lets us kind of lose information about any other particular interesting event that is happening. So I don't want that. Let's make a little change to make this a little more kind of graphically pleasing and kind of show us more good information at the same time. So see how we're just kind of very easily, naively echoing whatever event is happening right now. What we could do instead is to recognize that if we had 2 consecutive clock signals, see, we used this naively before to counting pulse delta, but we can use that same thing to say, oh, if we are in a clock delta and the other was a clock delta, let's not advance to a new line, but just overwrite on the same line. And if we actually pop the stash right now and start our program, what are we going to get? That looks way nicer. Now we don't lose our place that easily. We're gonna always see the clock signal just right there as one event, unless there is another event. So if I actually played a few notes for you, see, like those notes appear as nice events, and now you can actually decipher them. Before they would just kind of float away very quickly. So now if we start, you will also see a 250 and 252 message being sent. So yeah, 250, let's start. 252, let's stop. Way nicer. This is going to make our later experiments much easier. So let's just stop the process right here and just kind of play with this for a second. So whenever I play with advanced Python programs, very often I end up both importing itertools and random. So let's just do both like right away and use them somehow. So one thing that we didn't do yet, but we can now and we will, is kind of play with the volume of the play drum. So here the volume is always 127 if we don't specify it. But what if we actually had some kind of a volume specified right here? So we could have, for example, 127, 95, and 63. So those are just three. And to make this actually do a thing, we can now do a volume equals itertools cycle through volumes. So just having them cycle already causes us to have issues, because I need to put this obviously as an iterator. It's itertools. So we need a volume in itertools cycle. That's the danger of narrating and coding at the same time. Like, you are skipping steps. That's why I didn't want to do the entire presentation like this. That would be very annoying to you as a witness to that failure. Anyway, that is already cycling through volumes. Let's see how that sounds. So it already creates this kind of echo effect every 3 notes for us, but it'll probably be easier to hear if it's also out of sync with the snare drum notes. What that is typically called is polyrhythms. So the different kinds of tracks that you're having, the different instruments are going to be playing in different meters now. But what they will agree on is the clock. So that actually already sounds rather rich with very minimal changes. That's already pretty interesting, right? There's some richness to what we're doing, and we can add even more to it if we slow down the snare drum twice, right? So having it not rush as it did now creates this kind of trappy, drum track for some kind of musical tune, right? So now it already floats a bit slower. With very little code. We could obviously just tweak this further. We could, for example, just decide that we might randomly either keep doing this here, like, or either skip it or just, rest for a while. So for example, we could just choose, like, if random is bigger than half, right? So half the time we will be doing this and half the time we won't. We will wait. How long should we be waiting, for example? Since this is 24, 12, and 12, we can just wait for, say, half of that, so just 12, to reorder the hi-hats somehow. Let's see how that works now. Yeah, so this already kind of gives us some richness of the drum track with very minimal coding. But it's just the drums, and the mono station stays here like rather bored, not doing much. Yes, I agree with you, this is not perfect. We need to make use of it. So to make use of it, let's get to the next step. Let's stash our wonderful sequence right now, stash, and move to the next step. That's going to be the 15th step, and probably the final of our play with Git. Now we're only going to do some more coding right here in Visual Studio. So we already have a bass line. Let me just restore our drum track so I don't forget. And having that, what changed? First of all, we had a play a drum high-level function. I created a plays bass function that we can use as well, so that it is just a single line that we can use to make sounds happen. So that already works. And now, whenever we are getting our start and stop signals, before we were just creating a task for the drum machine. Now we are also creating a task for the bass line as well. And similarly, when we are stopping, we will be starting the drum machine, canceling the drum machine and canceling the bass line now as well. Also silencing it. So that is it, essentially. Now the task is called analog synth because it is an analog synth. And so far, it doesn't do much, just as our drum machine didn't do much at first. It just plays one C2 note every 2 quarters, so every half note, with some decay of half, which is the default, but we can play with that to see how that changes. So there's going to be some music intervals here that I'm going to be using right now, but don't worry if you're not familiar with the music theory behind this. That is something that we can kind of talk over later on. If you're interested, I can explain in a separate communication channel. So now let's see what this does. Okay, plays every second note as promised. Not much is happening, but because of the filter that I can play with, it's already pretty rich. Okay, but we're here to code Python, so let's make the baseline a bit more interesting instead. So we have the baseline right here just in a while loop as well. And since it's a monophonic synthesizer, you might be thinking, well, there might not be much that we can do with this. But in fact, that's not exactly right. What we can do is we can change the decay here to 1.0, which is something that the real musicians in real instruments are unable to do. You cannot really just press a note and hold it for 100% of a quarter note and switch immediately to another quarter note. This will just not work for us. But these are computers, and we can actually do this. So what we can do is, again, cycle through a bunch of notes, and by doing this, achieve some arpeggiation, right? Like those things are usually called arpeggiators. So the notes that we would be interested in would be, say, the C1 at first, but later we can just say, let's just add some intervals to it. So if I switch for a second here, if you look at the notes right there, this is going to be one C note. If we add a perfect 5 to it, we're going to get to a note like this. It's going to be G, right? If we add 12 instead, we're going to go from here to here. It's an octave. And same if we add an octave and a perfect 5, we're going to get to here. So we can do sequences like those. And this is something that synthesizers are known for. They're very often used in combination with an arpeggiator, because then you can kind of make a lot of richness just happen on the filtering and envelope side of things. So let's attempt something like this. We can actually add another octave right here. And we can add an octave and 4 here, perfect 4. And we can add an octave and a perfect 5 here, and then we can just add the perfect 5, so it's going to be an octave perfect, an octave lower than the previous one. This is also kind of exciting because those are 5 notes, so again, this is going to be a polyrhythm if we cycle through it while note, while 4 note in iter tools cycle notes, and the note that we're going to play is just note. But let's just make them very quick instead and see what happens. Again, we need to start. Pretty cool, and just one thing happens at the same time. But even monophonic synthesizers can actually allow you to play a note and then play things over it. So if we play a bass note right here and keep pressing the note on, now it doesn't work because I disable sustain, but if I keep sustain, it keeps playing. And I can play other notes over it and then stop playing them, in which case it will return to the first note that was being played. So we can actually do this now with the arpeggiator that we worked in here. Just again have some coroutine for the bass note, right? So it's going to be the bass, kind of it sounds the same, but I meant a different word. Bass note right here, and this is going to play just our bass note every, say, 96 pulses. So performance play bass C1 every 96 pulses with decay of, say, like, let's just leave the 1.0 so that we hold on to it for a long time now. And now the arpeggiator that we have here, async def arpeggiator, is going to be a separate coroutine. But since we already play C1 as well here, what we can do is just to make sure that there's a bit fewer of the C1s. In fact, we maybe want to add 2 octaves here. And here we want to add maybe another 2 octaves. And to keep this out of sync so that something more interesting is happening, I can just add just 1 octave here. So it's 5. And now this is going to play, but if I play it with full decay, that would actually not do anything interesting. So let me play with half of decay. So we're going to be coming back to the bass note every half. And maybe interestingly, if we had another note that would be, say, none, right? So rest, we will not play anything. So to play, thank you, MyPy. If there is no note, so if note is none, we don't want to play, we want to wait. So we're going to be waiting for 6, but otherwise we will be able to play a note. So see, now MyPy is happy. We have successfully used the none value in a conditional, so we will never get to none right here. Good job. Cool. So again, if we just leave it like this, nothing would play because we need AsyncIO gather to do the bass note and do the arpeggiator as well. Cool. So let me start this and start our thing and to see how this is going to sound. If there is no sustain, the bass note is not playing. And now, interestingly, we can also do stuff like add some kind of glide between the notes, which the synthesizer supports. right, pretty sweet. But what I would still like to show you is that this can be interactive in more than just a sense that I can just twiddle the knobs here. I can actually do like influence our sequencer from code as well by playing some other keyboard. Like, this particular instrument also has another synth that is silenced now, right? Synth 1 is the pink one. So I can just use it as a keyboard. And it would be great if that keyboard influenced what is happening on our sequencer here. So let's attempt this, right? Let's do something with that. So let me first remove maybe this particular octave right here, like the perfect 4. But instead of just having the C note right here, like, would it be great if we just got whatever note I am playing on a keyboard right here? So to achieve this, the only thing that we need to do, like, fortunately, is to react to another kind of message, right? So to do this, let me just type it in right here rather quickly. So the thing that we need is to react to a note on event, right? Just as you would kind of expect probably. So note on. And what are we gonna do with this note in this receiver? Well, we don't actually have any access to the sequencers, but we have the access to the performance object. That is good enough. Like, let's just store the last played note in that object. So performance last note would be the first message, the other byte of that MIDI message. Right, so cool, but now MyPy isn't happy with me because performance does not have a last note attribute yet. Good job then, let's do that. Let's use our last note as just an integer here. And to avoid having to, kind of either make it optional or to deal with this when we're creating the performance object, let's just say that the last note initially was 0, right? Or in fact, maybe we can just say it was the same note as we had on the base C. So what's C1 again? C1 is 36. So let's just set that to 36, like initially, just so that there is some sensible value. So now we are not using perfect fours. That is true enough. We can, instead of playing C1, we can play the last note being played. So we can, for example, do performance last note. But to be able to influence this a bit faster than just every 96 pulses, let's just do 24 so we can make changes more often. Okay, so now we're playing the last note here, and maybe here we can also just set up one of those notes, not both. Like, let's just set up one of those notes. So instead of C1, we're going to say performance last note. Cool. So now let's check what is going to happen when we're playing. Okay, you can hear that definitely we are influencing this in some way. The one thing that is kind of annoying though is that at the first start of the sequence, we would like to hear the bass note and not some random arpeggiator. So what I would like to do is to make sure that when we are iterating over our iteration, like every 4 notes, right? So in the in sequence of what is playing musically, we would like this to just always wait, just so that we can have an opportunity to hear the main bass sound clearly. So this is, interestingly, again, rather simple to implement with Python, because you need to just enumerate over whatever is happening here. And you're going to get an I right here. And now the only thing that we need to do is make sure that if I, and we're going to get those notes every 6, so there's going to be 4 per quarter. So if we want to do the first quarter, is going to be 96 divided by 6. So if we have the current, if the note is none, or I modulo our 96 by 6. 96 by 6. Then we're waiting. Otherwise, we're going to be playing our nice arpeggiation. In fact, we can actually maybe just remove that from here so that always there's going to be some arpeggiation, not when we are playing. Okay, let's see. Pretty cool, right? So the thing is this. This particular thing took us an hour to write, right? Like with an explanation. So probably, you could get it at the same time while trying to figure things out when they don't work. And now the sequencer here is, both for the analog synthesizer and for the drum machine, fitting a single screen of code. They're very easy to understand, like from the perspective of an AsyncIO programmer, and very hackable. So you can do sequences of notes that will do some interesting relations between intervals and between rhythms and whatnot, like with minimal trouble as a Python programmer. So with this, you can make self-generating music that is going to be different for hours on end. You can create sessions that will not be boring, but still will remain musical for hours on end. So it's a very powerful technique to do programming like this. So just for me to not lose what I just wrote so that you can actually use this like yourself, let me just see what were changed. Yes, AsyncIO tone main. Let me just commit this for you. So final stage. Having that commit, cool. That's on the PyCon branch. Like we can actually move to the main branch that I have here, just to show you one more thing. This is deleted now, and it actually annoyingly maybe changed to black because that's how I usually code when I'm not recording videos. What I wanted to show you is that there are two things here. Like there is the circuits module that is doing what we were discussing here in this video, but there's also a red-blue module. And that module in particular is enabling me to interact with my Moog synthesizers that I showed you in the slide before, in ways that would be otherwise very hard to do. So I already told you that a monophonic synthesizer only plays one note at a time. If you have more than one of those, you could actually make them switch between each other and achieve polyphony. This is exactly what I did with my Moog mother synthesizers that I have, the modules that were black in the picture. So just to get there, I just named one of them red and the other blue because that's the colors of the MIDI cables I had for them. And you could now use this as an instrument that, just multiplexes MIDI messages coming from a MIDI keyboard and does very interesting musical effects as a single instrument, even though you're interacting with multiple hardware synthesizers at the same time. I'm using this all the time in my music. All right. So at this point, we are at the conclusion of our particular talk. I hope this was useful. That went way over time in terms of my 45-minute slot that I would get in Pittsburgh. And even though there I also wanted to teach you AsyncIO at the same time. But I hope that through going slowly, through the process of creating all of this from scratch, it became much more natural to you. So there are no magical moments in it, and you understand how the pieces connect together. And even if the particular synthesizers that you have on your own, in your own setup, are different, there might be not the Novation circuit and the monostation, you can still take the code that we just wrote and use it for your own musical purposes. At the same time, I do hope that this was a good way of explaining how AsyncIO works. I always found it kind of ingenious and maybe a bit annoying if you just had dry examples like time sleep becoming AsyncIO sleep, because they are very far from any sensible, reasonable use case that you might have in the future. And if you're using AsyncIO for web development, for a REST framework, or for GraphQL or anything else, you would be able to maybe imagine that, oh yes, this will handle 10,000 clients at the same time. But it's hard to actually hear things, right, or see things happen at the same time and understand what that means for us. Here you could see that there were multiple very easy coroutines which were executed concurrently using AsyncIO, and they were doing very many things for us. Just the drums, those were 3 tracks, right? We had the bass drum, the snare drum, and the hi-hats, just going freely out of sync, using polyrhythms. They were using something like rather advanced to just type in manually. That was self-generating. And same for the bass line. We had a rather advanced arpeggiator right there that did respond to our notes that we were playing and sequencing in real time. So kind of a good presentation in terms of tactile feedback, right? You could see those things actually happen as I was showing you the synthesizers, pressing the notes, playing with the filter and whatnot. So thanks for actually getting through to the very end of this rather long video. I hope that you won't be late for your next talk. That's it for now. My name is Łukasz Langa. Find me on the internet. See you next time.